So, but even these there's no guarantees of how well these are going to work. You can show that they'll converge to a local optimum, but that's it. Okay, but what's the nice? So there's one really nice property I want to point out about this formulation. Okay, so one really cool thing. So we talked about clustering for several lectures in class. And so this is really a clustering, right? This is a graph clustering. I partition the data. It's a hard clustering. I partition the data in these k different parts, and I've optimized some score. So I don't even need to specify this k here, right? I can say, break this into these set of communities. I don't care how many. And I know that if I put them all in one thing, I'm going to get a score of 0, or I should if I get the formula. I think I remember that there's some kind of term here you need to multiply this by so that this cancels here. There's some kind of extra term. I'll try and look it up closer. So assume that if I have the whole vertex set, this property is 0. And also you can see if you have individual edges, vertices by themselves, any individual vertex is also going to have a score of 0. So the sum of them will also be 0. But I should be able to get modularity, which is positive, right? And that I did not need a choice of k here. Okay, so every other clustering algorithm we talked about either needed some parameter of how to of kind of when to stop. There's some density versions, or there's some k and k means clustering, for instance. This form of this does not have any sort of parameter limit. It's kind of a pure optimization problem. It doesn't tell you how many clusters to have. So this is pretty cool, but it's not really easy to actually find the optimum. So there are various heuristics. You can run different algorithms with, say, run spectral clustering until you get k clusters and then try and optimize this. But there's no guarantee that's going to give you the right answer. But you're probably going to bias towards having this number of communities that you started with. You could say combine 2 communities as one of the potential search steps you do. You're probably going to be biasing towards that value k. And actually you find, people have looked at this and found local optimum at many different sizes of number of communities inside of it.
This looks like an NP-hard problem.
What?
This looks
Yeah,
like
it's probably NP-hard. I don't know for sure, but you're probably right. I didn't look that up. So great. So we'll have one more lecture on Monday. We'll talk about how to we'll talk about different properties of graphs, how to do graph sparsification. So how to preserve properties such as these of graphs while removing most of the edges, and why that's an interesting problem. So that'll be Monday, and then poster session is Wednesday.